So for us, simple harmonic motion is really describing what pendulums do with this idea of it moving back and forth with more or less constant motion, or oscillating springs, where again they're moving back and forth or up and down with an ideally repeating motion. So the first lens that we're going to look at it through is the first lens we kind of learned to look at a lot of problems through, which is through the lens of forces and a little bit of kinematics. So let's start with the pendulum. And with the pendulum, I'm just going to draw the forces that act on it on different points. So at this point up here, we would definitely have the force of gravity, mg, acting downwards. And then right along the direction of the rope would be the tension. So if I wanted to describe the direction of the net force is going, roughly maybe something in this direction. That's both the net force and the acceleration. And so you can see that as it's going up towards the left, it would be slowing down on its way up. That's because the acceleration is opposite the velocity. And then once it gets to that highest point, it starts speeding up back this way because, again, the force and acceleration are pushing it back towards the central position. This is what's called a restoring force that's trying to get everything back into the equilibrium position. On the other side, the story is much the same. Tension now is going up and to the left. Force of gravity is exactly the same, but the acceleration and the restoring force are just trying to push it right back where it started from. So from a force perspective, we always know that the acceleration and the forces are going to be pointed in a direction that more or less points towards the equilibrium position. The weirdest thing about pendulums is that in the center, they're not actually in force equilibrium if they're in motion. Because if this is in motion, then what we really have right at this central position is we actually have centripetal acceleration. The velocity isn't changing right there, but the speed isn't changing, but the direction is. So since the direction is changing, the velocity actually is changing. So we have centripetal acceleration. And if there's centripetal acceleration, then it has to be going towards the center. And if I draw this free body diagram, that means I have to have more tension and a little bit less force of gravity acting on the system. So in the middle, there's always a centripetal acceleration. And I'm going to do a quick derivation to show you the formula for that centripetal acceleration, although you do have to be given some some specific information to get exact values for this. So the first thing that I want to describe with this, how far do I want to get into this? Okay, yeah. Let's describe first the change in height. Let's call this, here, let me use a different color so it pops out a little bit more. Let's call this H. It's the difference from where it starts to where the lowest point is. And using that, I can figure out, this will be a little bit in the next video, but I can figure out the speed at the lowest point. 1/2 mv squared would be equal to mgh, the gravitational potential. And so if I manipulate that equation a little bit, the velocity would be equal to the square root of 2 times gh. Then if I wanted to talk about the acceleration right at that point, it's going to have centripetal acceleration. So that's v squared over r. That would equal the sum of the forces, T minus mg, all over m. This is the forces acting on it over the mass. So from there, I can manipulate the equation a little bit, multiply both sides by m, add mg to both sides, and I would get to a form that looks something like mv squared over r plus mg. This m is here because I multiplied both sides by m, and then this plus mg came because I added mg to both sides, and that would give me the time. And then I could put in this velocity, this velocity in there, which since I'm going to square it, is going to go right back to 2gh. And so I would find out that my velocity is m times, let's call it um, 2gh. Sorry, I lost track of my train of thought. Over r plus m, g equals t. And then we could clean this up a little bit. It turns out that I could pull out both the g's and both the m's, and I could get that the tension is going to be equal to mg times, let's see, how does this go again? 2h over r plus 1. Does that look right? Is that what I got last time I did this? I think so. Yeah. So that's gonna depend. We need to know what H and R are. So we'll get different values, but that's a useful derivation that may be coming up on your AP exam at some point. So now you know how to do that. So that's what we really need to know for simple harmonic forces for pendulums. The restoring force pulls it towards the middle, and there is a centripetal acceleration. And now we even know how to solve for time for the tension. For the other piece, this for springs going back and forth, it's a little bit straightforward. At the furthest point out, right here, it's going to have gravity acting on it if it's a horizontal spring, like going back and forth. Usually they say it's on a frictionless surface. So then we would have normal force going up and the force of friction, the force of the spring trying to pull it back. Just so you're aware, if there was a force of friction here, this immediately stops being simple harmonic motion, and we can't use any of our formulas anymore. We would just use some kind of conceptual description of like, all right, well, it's not going to accelerate as much as it would if friction didn't exist. It's going to stop eventually. It's going to be moving a little bit more slowly than we would expect with the ideal equations, that kind of thing. At the point that it's maximally compressed, the same force of gravity and the same normal is acting on it. But this time, spring force is going to be equal in magnitude to down here, but this time pushing it back towards the middle. And then right at the equilibrium position, we would just have force of gravity and normal force, but no spring force because it's not, the spring hasn't been stretched or compressed, which means there's no force acting there. So for these problems, again, you should notice that there is a restoring force that's always trying to pull the mass back towards that equilibrium position. The only difference here between, or the biggest difference, is that at this equilibrium position right there, we actually have a sum of forces and an acceleration that's equal to 0, which we didn't quite have in the pendulum case because we needed the centripetal acceleration to cause the change in direction right at the very bottom. So for your information, for just a reminder, we can find the acceleration in these problems. If they gave you how far it was pulled back, and if they told you friction even, you could calculate the exact acceleration. But because the force constantly changes, you can't do anything with kinematics with these problems. You can only figure out instantaneous acceleration, and then it's up to energy equations or the simple harmonic motion period equations to figure out how long it takes to go back and forth. For the vertical springs, the problem gets a little bit weirder because we have some other forces involved. The first big force that we obviously have involved with a vertical spring that was there in the horizontal spring, but just didn't really matter because it was at a right angle to the acceleration, was the force of gravity. We have a force of gravity in all of these scenarios. Now, what typically gets told to you in a vertical spring problem is they'll usually say we release it from the position where it's at rest. So usually x min here is actually the natural length. It's not always. They'll describe the problem well enough that you can tell. But if they don't really point it out to you, it's probably because they've said somewhere that that's the natural length, which means at that position there would be no spring force acting on that. So I'm making the assumption that x min is the natural length, and that's why there's no spring force in that first free body diagram. But then as it starts going down and it gets to what actually is the equilibrium position, we would have a spring force going upwards. And at that equilibrium position, the spring force up and the force of gravity down would be equal, but it doesn't stop because equal forces don't mean nothing's moving. It just means it's moving at a constant velocity. And since from x min to 0, it had a net force going down, it's been accelerating all the way down to that equilibrium position, which means it has a lot of velocity that it doesn't lose until we start going the other direction. And as we extend this spring further and further, the force of the spring is going to get greater and greater and greater, eventually slowing down and bringing it finally. So if we started at a natural length, it turns out that the force of the spring will always be equal to 2 times the force of gravity at that furthest position down. But that's only if we started at natural length. If we let it hang and then we moved it up a little bit and let it go, then the way this is going to work out, you'd have to do a little bit more mathematically. But that is a rule of thumb you can use if it ever helps. Last thing I want to point out is this equilibrium position is not the natural length of the spring like when it was horizontal. It's the spot where the force of gravity, Fg, and the force of the spring happen to be equal, so that if you let it go, those forces would balance out. The horizontal spring didn't have to do that because there was no opposing force to the spring. If you just put it in the spot where the spring was relaxed, there was nothing for the spring to work against, so it just stays there. Vertical spring, it's force of gravity versus force of the spring. So that's everything you need to know about simple harmonic forces. A lot of information in here, and it's going to be really useful for you to be able to describe all of this stuff on your own. But really, all of it is stuff that you already knew about, with the exception that we kind of introduced Hooke's law. So mathematically, you can do a little bit more than you would have been able to do with just free body diagrams before today. Thanks for watching.